Hi, Year 11. Today we're moving on to 10E, which is looking at the consequences of the factor theorem. Now, today's work starts to get a little bit harder, and so if you haven't had a good go at 10A up to 10E, you need to go back and make sure you're very confident with factorizing and understanding how a polynomial is a combination of a divisor, a quotient, and a remainder. You need to know the factor theorem, you need to know the remainder theorem. So if you're not ready for this today, then you need to stop this video, go back and make sure you feel confident with the other work. So we're basically going to incorporate all of that together today. So I've just jumped over into our OneNote under 10E, the consequences of the factor theorem, just to have a little walk through some of these parts in here before we go through our notes today. Now, there are lots and lots of consequences of the factor theorem, and a lot of them are written in a fairly complex form. A lot of them are actually self-explanatory, and when you read it, you go, yeah, I know that. So I'm going to go through the ones in the textbook, and then we're going to basically work through some examples, and some of these start off fairly easy, but I want us to have a look at some harder examples as well today. So consequences of the factor theorem. Before we do that, let's just have a look at reminding ourselves what the factor theorem was from yesterday's lesson or the last lesson that we had in 10D. So supposing that, the factor theorem says, suppose that p of x is a polynomial and alpha is a constant, then x minus alpha is a factor if and only if p of alpha equals 0. Okay, remembering that x minus a is linear. If we pop in our alpha or I think I had a in the one that I had, x minus a, if we pop a in or alpha into our polynomial and we get 0, then it means that it's a factor of our polynomial, which means we've got no remainder. Okay, and that would give us a 0, basically. So that's what we're looking at, and we're going to have a look at the consequences of those today. So let's look at the first thing here. One of the things our textbook looks at is saying that supposing that alpha a, alpha 2, up to alpha s are distinct zeros of a polynomial, then x minus alpha 1, x minus alpha 2, so on, all up to x minus alpha z is a factor of the polynomial. And we know that from quadratics. So, for example, if we had x is equal to 1 and x equal to, for example, minus 2 are zeros of a polynomial, then we would know then that x minus 1 and x plus 2 are factors of that polynomial. So we know that. That's what that rule's saying. So that's one of the ones that I would call fairly self-explanatory. The next one. This is the one that I think we need to specifically make sure you understand. And we'll look at examples. So it says, supposing that alpha 1, alpha 2, up to alpha n are n distinct zeros of a polynomial of degree n. So here we had a polynomial that was a quadratic. It's a polynomial of degree 2. We had 2 distinct zeros. So if we were looking at a quadratic, we would have rephrase that again. If we were looking at a cubic, something that had an x to the power of 3, 3 is the degree. The polynomial will have degree 3. There'd be possibly 3 distinct zeros. Not always, but that's what we're talking about in this part here. So if there are n distinct zeros from alpha 1 up to alpha n of some polynomial of degree n, then we're saying that the polynomial is equal to some constant a times what we talked about up here, the factors, x minus alpha 1, x minus alpha 2, all up to x minus alpha n, where a is the leading coefficient of the polynomial. So I think the thing to note, the difference between these two is we're incorporating this a in here. So I want you to think about that one, and we'll look at those examples in a moment. 17 is fairly self-explanatory, the maximum number of zeros. So a polynomial of degree n has at most n zeros. So if we think back to our quadratic back here, a quadratic has a degree 2, it has 2 zeros. We can't have 3 zeros because it has a power of 2 or a degree of 2. 19, suppose that p of x and q of x are degree n polynomials that have the same value for at least n plus 1 values of x, then the polynomials p of x and q of x are identically equal. That one's fairly self-explanatory, and we'll look at some questions on that one as well. And this one I like to put in. They're not necessarily points the syllabus as saying you must know these, but they are implications and consequences of the factor theorem and things that you probably know, but you haven't actually thought about before. So let's have a look at the first one. The graph of a polynomial function of degree n is completely determined by n plus 1 points on the curve. So a polynomial of degree 2, so a quadratic, is determined by 3 points on the curve. So that might be where it cuts the x-axis, where it cuts the y-axis. Part 2. The graph of two distinct polynomial functions cannot intersect in more points than the maximum of the 2 degrees. So we think about that. If we had two distinct polynomials, two quadratics, for example, I have one quadratic that looks like that and another one that is wider and cuts like that. So graphs of two distinct polynomial functions, I'm just looking at quadratics here because they're easy to graph, cannot intersect in more than the maximum of the 2 degrees. So let's read it again. So the graph of two distinct polynomial functions cannot intersect in more points than the maximum of the 2 degrees. So if I had two quadratics, the maximum degrees are 2, so they can't intersect in more than 2 points. So let's draw ourselves another one. So if I sketch, for example, a quadratic and then maybe a cubic, let's see if we can get it to work with a cubic. Sketch the cubic over the top. Then I can see that this would intersect at 1, 2, 3 points. So that would tell us that the maximum degree of those two graphs would be the cubic. So I can find 3 intersections, which is actually really hard to find, but I can't intersect at 4. So that's one that kind of makes sense, but we probably haven't thought of before. And the third one, a line cannot intersect the graph of a polynomial of degree in more than n points. So if I had, again, my quadratic and I had a line through it, I can intersect in 2 points, but I can't intersect in more than 2 points. Like my, if I had a cubic, I can intersect in 1, 2, 3 points, but I can't intersect in more than 3 points. And again, they're fairly self-explanatory. Okay, let's go and have a look at some examples now back into our notes. Now, this is probably one of the most important consequences of the factor theorem, and I showed you this in 10D in the OneNote as well. We'll have a look at this again. So it's saying if x minus a is a factor of the polynomial p of x, then a is a factor of the constant term of the polynomial. For example, we have this polynomial down here, then we would be able to look at the factors of 6 because that's our constant term, and that would help us find the factors of the actual polynomial. So that's something that you need to know, and we're going to use this rule to help us find factors and hence factorize a polynomial when there are no factors provided for us. So if we're given a factor to start with, we can use our long division. But if we're given nothing, then we're going to have a look at that final constant term and see if that can help us out. So there's some steps here if you want to use them. I think they're fairly self-explanatory in what you would do, but you'd write the factors of the constant term down. You consider both the positive and negative factors. So of 6, we'd have factors of 6 and minus 6, 1 and minus 1, 3 and minus 2, minus 3 and 2. So they'd be our factors. We would substitute into the polynomials until 1 is a factor. So one of those factors of 6 that I've just spoken about would have to give us, once substituted in, a value of 0, and that would mean to us looking at the factor theorem that was a factor. Then we divide that factor by the original polynomials to find any other factors. So we did that. So let's have a look and see if you can do that again. If you can, or you think you can, pause the video and have a go. Otherwise, we're going to have a look at it ourselves now. So the factors of 6, we're going to have 6 and minus 6, 1 and minus 1, 3 and minus 2, 2 and minus 3. We're going to substitute those into our polynomial, and we'll call this polynomial here p of x. And to one of those substituted in gives us a 0. I think I mentioned this last time. I like to start with the smallest number. It just makes it a little bit easier. So I'm going to start off with 1 and hope 1 is going to give me a value. So I'm going to pop 1 in there. I'm going to get 1 cubed minus 4 times 1 squared, which is 1, plus 1 plus 6. Okay, this equals 4 doesn't equal 0, so that's not a factor. Let's try -1, see if that one works. So I'm going to pop those values in. Okay, so I've popped the -1 in, -1 cubed -4 times -1 squared -1 plus 6. Popping that in, being careful to note that when we cube a minus, we get a minus. I end up with -1 -4 -1 plus 6, which is 0. So then I know that I have x plus 1 being a factor of this polynomial. Now, there's actually a couple of ways we can proceed from here. We can continue to substitute in each of these values to see if there are any others that are factors. But because our polynomial is actually only a cubic, it's probably going to be a little bit quicker in this case for us to do long division and try and find what the quotient is going to be. So that's what I'm going to do. Because again, what we're trying to do here is constantly try and save time in our examination process so that you've got more time to get your exam completed. I might actually remove that and pop that on the other side so I've got enough space. So make sure you've got enough space. Okay, so I've just written it up to the side up here. We're dividing our original polynomial by x plus 1 because we knew that that was a factor, because when we popped in -1 into our polynomial, we got 0 as a remainder. So how many times does x go into x cubed? We get x squared times x is x cubed, x squared times 1 is x squared. And then we're going to subtract. X cubed minus x cubed is 0. -4 minus 1 x squared is going to be -5x squared. And these two values continue back down because we don't have anything to subtract from there. How many times does x go into -5x squared? It's going to go -5x times. So we end up with -5x squared minus 5x. Taking away the first terms, -5x squared minus -5x squared is -5x squared plus 5x squared, which is 0. X minus -5, which is 1x plus 5, which is 6x. And we've still got our plus 6 on the end. We now need to look at how many times x goes into 6x. It goes 6 times. So 6 times x is 6x. 6 times 1 is 6. We're going to do a subtraction and we end up with a 0. So this is good news because we now know that our polynomial p of x can be written as x plus 1, which we discovered to start off with was a factor. And now we have a quotient up the top there, x squared minus 5x plus 6. That is not our answer. What our question actually asks us is to find all the factors. This is one factor. We need to find the rest of the factors. In doing so, we can just factorize our quadratic, which we are very, very good at. So what we will end up with is looking for values that add to -5, multiply to 6. We're going to have -3 and -2. That is our answer. Okay, having a look down at the next part of your notes is talking about identical polynomials. And that was one of the theorems I showed you in the OneNote. Just written slightly different here. It's saying that if our polynomial p of x looks like this, remembering the numbers out the front of the x are our coefficients, so a of n x to the n plus a of n minus 1 x to the n minus 1. So we're decreasing our powers of x all the way down to our constant term, where our polynomial is not a 0 polynomial. And the same for q of x. It's just got coefficients relating to b. So q of x has b of m, x to the power of m, all the way down to our constant term at the end. And if that also isn't 0, so two polynomials, then p of x is equal to q of x if all of our coefficients in front of our powers are equal and n is equal to m. So if both these polynomials were powers of 4 and continued down such that all of our coefficients in front of our x's of varying powers were equal, then they'd be equal. And that's something that I think is fairly self-explanatory, and we've looked at equating coefficients of powers before. It's just written there for you in a rule form, which makes it look quite tricky, but it's not. We're going to have a look at doing that now. So it's got an example here, and it's saying evaluate A, B, C, and D in 2x cubed minus 3x plus x plus 1. And this is going to be equal to a plus 1 to the x cubed plus b, x plus 4 squared plus c, x plus 4 plus d plus 1. So we need to work out what our values for a, b, c, and d are. Okay, there's a couple of ways to look at equations like this with polynomials. Now, the first thing I want you to have a look at is actually have a real look at what's happening in this polynomial. Yes, we're finding a, b, c, and d, and there's an a there, b, c, and d. But here we've got cubics, we've got x's, and we've got a 1. So here we've got a cubic, we've got an x that's related to a squared, we've got an x, and we've got a constant term. So what you'll note here is this b out the front is acting differently to the a here. The a is a constant we add 1 to, and it is attached as the coefficient of the x cubed. But our b is out the front, and it's acting as the coefficient of the whole of x plus 4, and that's all squared. So I need to do a little bit of manipulation. In this case, what I would suggest is that we would most probably be wanting to open these brackets up. And as I have a look at this, I'm thinking that we're going to pop a little squared up here. Just bear with me. I think there's a little typo in there. So I'm actually going to play around with that right-hand side to start with. So I've still got my, I'll zoom in there, a plus 1 x cubed. But what I'm going to do is I'm going to open the brackets here. It's going to be b times square the first plus 2 times the first times the second gives me 8x plus 16 plus c x plus 4 plus d minus 1. I am now going to expand with the b's and the c's. It's going to be a little bit messy. Bx squared plus 8bx plus 16b plus cx plus 4c plus d minus 1. I'm going to get the coefficients in the right order now to go with their powered terms. So I'm going to have an x cubed. My x squared is going to have a b, but my terms with x in it are going to be 8b, because there's an x there, plus a c, and everything else is going to be a constant term. And that's going to be my 16b here, my 4c, my d, and my minus 1. So now that it's in that form, now I actually can equate coefficients. So out the front of the x cubed, is an 2 there. Let's grab another colour. Out the front of the x squared is a minus 3. Out the front of the x, in this case it's going to be a 1. And my constant term, which we'll make green, is this. Let's see what we can do as a simultaneous equation. So we're going to need to equate coefficients. So the blue part first, so 2 is equal to a plus 1. I've equated my blue parts out the front of the x cubed. So then taking 1 from both sides, 1 is equal to a, or a is equal to 1. We've got our first solution. Okay, equating our yellow parts. I might pop the blue here so we know. Let's do the yellow ones. Out the front of the x squared, I have a b and I have a minus 3. So minus 3 is b, and I write it as b is minus 3. Nice and neat. Out the front of the x, it's now our pink part. I have an 8b plus c is equal to 1. Now, I know what my b is, so it's going to be 8 times by minus 3 plus c is 1. 8 3s are 24, so minus 24 plus c is 1. I'm going to add 24 to both sides, so c is 25. Lucky last, let's do the green one. Okay, my constant term is the green, which is 1, and that's equal to everything over here, 16b plus 4c plus d minus 1. So 16 times minus 3 plus 4 times 25 plus d minus 1. It'll give us 1 is equal to minus 48. 4 times 25, or 2 25s are 50, 4 is 100, plus d minus 1. So 1 is equal to, we've got minus 48 plus 100, take away 1, we'll get 51 is equal to, d plus 51. Let's go minus 51, minus 51. So what we're going to end up with is minus 50 is equal to d. There's another example down the page that comes from your textbook, similar to the question above, and it's asking us to find a, b, c, and d, given that x cubed minus x is equal to, you have a look at this polynomial function on the right hand side, and they're equal for at least 4 values of x. Now I'm going to jump back to the rule that we had a look at in the consequences in our OneNote. And it says an identically equal condition. Suppose that two polynomials are degree n polynomials that have the same value for at least n plus 1 values of x, then the polynomials are identically equal, that is, they're equal for all values of x. So the degree n polynomials that have the same values for at least n plus 1 values of x. So going back to that question, that's basically what that question is saying. It's saying we've got a polynomial here on the left that is a cubic. We have a polynomial here on the right which is a cubic, and that is a degree n polynomial. N just happens to be 3, and it's saying here that they are equal for at least 4 values of n, 4 being 3 plus 1 or n plus 1. So that talks about that rule that I've talked about in our OneNote. So if you come across that, that's all it's meaning, is they're equal, and they're equal for at least 4 values in this case of x, as we've got a degree 3 polynomial. Now, we could do this question exactly the same as the one above. We go back here, so we could do it the same as what we did here. Okay, in that we could expand our brackets and come up with simultaneous equations and equate coefficients. That is probably the most straightforward and sensible way, because that's what you're going to probably be thinking. But there's actually another way to do it. It would be a little bit harder for this one up here to do it this way. I had a go at it and it just got quite messy. But for this one here, it's going to work okay. So it's saying for at least 4 values of x. So there are 4 values at least of x for which these are equal. So I'm going to go and try some values of x. So I'm going to start with x equals 0 and just test that one. I'm going to make sure that I'm looking at the left-hand side and the right-hand side. So when x is 0, the left-hand side is going to be 0 minus 0, which is 0. And my right-hand side when x is 0 is going to be a, and I'm going to have minus 2 cubed plus b minus 2 squared plus c times minus 2 plus d. So if I neaten that up, I get 0 is equal to minus 8a plus 4b minus 2c plus d. That's an equation. Let's see if it helps us. At this point, it's not. We're going to need to find some more. So that's what happens when x is 0. Let's just try x is 1 and see if that helps us in any way. Okay. When x is 1, the left-hand side is 1 minus 1, which is 0. My right-hand side is going to be a times, we've got 1 minus 2, which is minus 1 cubed, plus b, lots of minus 1 squared, plus c, lots of minus 1 plus d. If I neaten that up, I end up with 0 is equal to minus a plus b minus c plus d. There's another equation. Doesn't help us yet because we've got 4 unknowns and we'd really need 4 equations to get that to work. What's going to give us a little bit of a neater equation is x is equal to 2. The reason why that's going to give us a nicer equation that's got less terms in it is when I pop 2 in here and get 2 minus 0, A and B and C are going to go to 0. So it's going to give us a value for D. So that's going to make our equations a lot nicer. So let's pop 2 in. So 2 cubed, which is 8. 8 minus 2 is 6. So my left-hand side is 6. My right-hand side, this part goes to 0. This goes to 0, this goes to 0, and D is equal to 6. So tick, we've got D. That would make our other two equations a lot neater. So we could pop those in there if we would like now. We're adding 6, so we'd get a minus 6 on that. So I'm not going to do that yet, but something else that I can actually do, which is similar to the equation above, in the example above, is coefficients of x cubed can be equated. We can easily do that in this case because the left-hand side's easy. There's just x cubed, it's just 1. But on the right-hand side, there's only one set of terms with a cubed in it, and there's only going to be one value where x is cubed. So I know that my leading coefficient is going to be a times x cubed. So 1 is going to be equal to A. Okay, so tick, I've got 2 of those down. So what that will mean is I can make these two equations here, 1 and 2, a lot neater. So let's neaten them up. I'm going to have 0 is equal to minus 8 plus 4b minus 2c plus 6. Okay, neatening that up, minus 8 plus 6 is minus 2. So if I'm adding 2 to both sides, I'll end up with 2 is equal to 4b minus 2c. So that's, we'll call that equation 3. And let's neaten this one up here. So I have 0 is equal to minus 1, because a was 1, plus b minus c plus 6. Minus 1 plus 6 is 5. If I take 5 from both sides, I'm going to get minus 5 is equal to b minus c, and that is equation 4. So we now have two simultaneous equations, being 3 and 4, that we can work with because we've only got two unknowns in each of them, and they're the same unknowns. Okay, there's a few ways to work these out. I need to work with 3 and 4. Pause the video, see if you can come up with a b and c. I'm going to change 3, and I'm going to halve each of the terms because I can pull out a 2. So I'm going to end up with a 1, a 2b minus c. I'm going to work with these two because what they are, they're both a minus c. So if I was to add both of those, that would give me my solution. Okay, so what I ended up doing was going equation 5 minus equation 4, and I ended up with b is 6 and c is 11. So I ended up with my coefficients, and a little bit messy there, of, what have we got? D is 6, A is 1, B is 6, and C is 11. So you might find that that's just another way to think about working out the solution to that one. But I think the best method is probably going to be this one up here, where we're expanding and equating coefficients. That'll get you through now to the next exercise, but I'm going to post this video and I'm going to pop another one up with some harder examples that'll align with the OneNote.